Hello and welcome to this video on equations of planes for the Further Maths course. So we thought about before finding the equation of a line using vectors, and now we're going to look at equations of planes. And there are different forms that you need to be able to move between. So the first one, the vector form, is r equals a plus lambda b plus mu c. And r is a position vector of a general point in the plane, a is a point in the plane, and b and c are non-parallel vectors. So what does all that mean? That means that you get onto the plane by some vector a. So suppose we get on there. So that's the vector a. Now I'm on the plane, but I want to be able to move around the plane. So I might want to go in a direction b, and that vector must be in the plane. Take me somewhere in the plane, but it's no good just being able to do lambda lots of b, because then I'd only be able to move in this one line. I also need to be able to move c. Both of these vectors are flat in the surface of the plane. They may not look like it at the moment, but that is what they are. So it's important these two vectors aren't parallel, otherwise you won't be able to get all over the plane. So this is the vector form of the plane. There's another Cartesian form of the plane. And really, this is a topic where once you get to the end of it, it's worth coming back and thinking about the beginning of it again. But this is what the Cartesian form of the plane looks like. And you know this from the work you did in the last chapter. If we've got a normal vector for the plane, then if we take the normal vector and use it as the coefficients of x, y, and z, and put it equal to d, and the significance of d will be explained in class later on, that gives you the equation of a plane. So n1 times x plus n2 times y plus n3 times z equals d, or minus d equals 0. That's how they tend to write it in the formula book, where n1, n2, n3 is the normal to the plane. There's another form called the scalar product form. Now, this is r dot n equals d, where d is a dot n. Now, this all will sound a bit strange at the beginning because you don't know what the scalar product is yet, but we will cover that in the coming lesson. So if you just cope with it for the moment. So we've got to find an equation of the plane through that point and perpendicular to 1, 3, 2. And just reassure yourself that this does define a plane, because if I've got the perpendicular to a plane and I know a point on it, then I can imagine what that plane is going to look like. So this is the normal. We want the Cartesian form, so we're going to use this here. So we're going to say 1 times x plus 3 times y plus 2 times z is equal to d. Now, we don't know what d is, but we know this point is on the plane. So if I substitute in this for x, y, and z, it will work. So I get 2 plus 3 times 3 plus 2 times minus 1 equals 9. So the equation of the Cartesian equation of this plane is x plus 3y plus 2z equals 9. Suppose I want the scalar product form, well then that's going to be r dot the normal, and the normal vector is 1, 3, 2, equals d, and d is a dot n. Now don't worry that you don't know what any of this is at the moment. A is a point on the line, on the plane, so that's 2, 3, minus 1, dot the normal, 1, 3, 2. So this dot is an operation. And you actually work it out. It's very easy to work out the dot product for these sort of vectors. You just multiply each pair of numbers together and add the total up. So you get 2 plus 9 minus 2 equals 9. So this 2 plus 9 minus 2 equals 9. The equation of the plane can also be written as r dot 132 equals 9. And that's another form of a plane. That's another way of writing the equation of a plane. So look at example 2. It says find the equation of the plane that contains these two lines. So what we've got going on here is we've got a plane and we've got two lines in it. So we've got maybe one line that's lying in the plane like that, and then another line that's lying in the plane like that. And those are going to give us our direction vectors. So for this one, it says find the equation of the plane. It doesn't tell you which one it's going to be, but we're going to do a vector equation of the plane. So r is equal to a point on the plane. Well, we could choose either this point here, or we could choose this point here, because these lines lie in the plane. So if my origin is here, and that's my point on the plane for this line here, that will do for my point on the plane, 2, 1, 1. And then I need two non-parallel vectors. So I'm going to have lambda times 2 naught minus 3. So that's the direction vector for this line, plus mu times the direction vector for the second line, which is 1, 1, minus 1. We could have got onto the plane with this vector here, but that gives us an equation like that. So when we've got r is a plus lambda b plus mu c, these are two vectors in the plane. So these are vectors in the plane, and this is a point in the plane, a point on the plane. And that gives me the equation there. Let's just look at the last example and I will talk you through that. So for this example, it says find an equation of the plane that contains these 3 points. So if we've got 3 points, that defines the plane. So we've got 3 points here, P, Q, and R, and we want to get it in this form here. So we need a point on the plane and two vectors that lie in the plane. So they're going to find PQ here. How do I get from P to Q? So they do it by working out OQ minus OP. So we know that that's PQ. How do we get from Q to R? We've got that vector there, and we work that out a similar way. So we want a position vector of a point in the plane, so we could choose any one of these points. Doesn't matter which one we choose, but they've chosen P. So the vector equation of the plane is going to be get onto the plane, so 3, 1, minus 2. And then you're going to have lambda lots of PQ plus mu lots of QR. So R is going to be 3, 1, minus 2 plus mu times PQ we found up here, minus 2, minus 1, 6 plus, lambda times that plus mu times minus 3, 3, minus 5. And that is the vector equation of this plane here. So there are different forms of the plane and you use them in different situations. You need to be able to move between the different forms of the plane with reasonable confidence.